אני לוקח משם ממש בלי אשמה. מה זה בלי אשמה? אני מרגיש שמגיע להיות אחרי הסמסטר הקודם.
גם מסלול.
לנו היה פאני בלי...
למה אשמה?
כן, לא, כאילו...
שצריך להתחיל.
השם שהוא לא לוקח יותר. כמו שאתה אכלת בסבבה.
לא, רציני, לפעמים זה המין מסלול, לפעמים מסלול.
צריך להתחיל לגנוב גם מהתיאור.
מה אתה אומר?
זה נגיד הייתה לי טיפה אשמה.
לא יודע,
לא שזה הפריע, כן.
שמה?
היה אשמה, אבל היה לי גנב.
מה שמה?
מהתיאורילנד.
לא מה, תיאורילנד זה גאווה לגנוב מהתיאורילנד. הבעיה היא שעכשיו הם עשו את זה קשה. תקשיב, אני לא מבין מה זה המדיניות הן גנבות האלה. הם עושים את העמדה של האוכל ליד ההוא עם הלוח, שאתה לא יכול לגנוב מהלך ההרצאה. אתה צריך לבוא עם בגדים, להתחפש לעתיד.
מה המפריע שהיה זה בשמה? וגם היה רמת קפסולות של קפה.
רמת קפסולות של קפה?
רמת קפסולות של קפה.
אז כאילו מי שבא לפני, אז מכין לו קפה
איפה עדיף? אחרי זה הוא שואל למה סטודנטים לא מגיעים למדרשה. יש פה 1,000 סמינרים, כל אחד יש פה כיבוד.
רגע, גיא, זה מוקלט? אחרת אולי אפשר לשלוח את זה לנציגות בפקולטה. זה מוקלט, כל הריחולים שלנו פה, יש לנו טענות, אולי נשלח את זה לפקולטה ישירות. למזכירות.
יש עשיתי הקלטה אוטומטית.
אז בשביל ההקלטה, מי שאמר את הדברים האחרונים זה... זה היינו פעם שעברה, דיברנו. So last time we showed that, so let me remind you, a star representation, okay, there is a problem with the television, turn it off.
יכול להיות שעשית סיסמה חדשה, אביב מנסה להתחבר.
The password is operating. I send them everybody. הכל בקצרה. So we will just remind that star representation is nothing but star homomorphism into B of H. And there are the irreducible star representations that are those for which I cannot find a closed subspace K of H such that pi A of K is in K, such that K is pi A invariant. Is irreducible if for every or there is no K strictly between H and 0 such that K is pi A invariant. And we also showed that pi is irreducible if and only if the commutant of pi A is, well, the minimal thing it has to be. I mean, it has to contain the constant. If it contains only the constant, then it is equivalent to irreducibility. Okay, so just a quick remark. What happens if we start with a C-star algebra that is commutative? Then who are its irreducible star representations? So why? So the character R means multiplicative linear functionals. Why? So no, I'm saying it's written here. If if A is commutative, just turn off all the notifications.
Pi of A is fine. Contains pi of A.
Who are the irreducible representations of a commutative sister algebra? So if A is commutative, then as I said, from this theorem, for example, we see that right pi of A, if A is commutative, then pi of A is commutative, and of course it must commute with pi of A, so it will be in the commutant pi of A.
גיא, מישהו שואל אם יש סיסמה חדשה לזום.
מי זה?
לא יודע. אבל ענית לו?
אם זה
זווית.
אז אני אקרא.
כן, אוקיי, sorry.
But so if pi is irreducible, right, then this is nothing but a constant. So if pi is non-zero, it means that the dimension of H is 1. So if pi is 0, then right, then dimension of H. So these are the one-dimensional representations. Yes, sir. Okay. Now, so let's go back something like to the 60s, like 50 years ago, or to the 70s. Then people thought that if irreducible representations, so what are the, so if A is commutative, what it means that the irreducible representations are exactly the one-dimensional ones, meaning these are exactly multiplicative linear functionals. What are multiplicative linear functionals in the or characters for the algebra, sister algebra C of X? Well, it is evaluation at the points X, right? So right under the isomorphism of A with maybe C naught of X. Okay, if it's not commutative, if it's not compact, if it's not unital, the irreducible representations, star representations, exactly corresponds to points.
Is it clear that we don't have anything else?
What?
Is it clear that we don't have anything else?
Yes, I mean it is clear to show that any, well, from Riess representation theorem, you know that all the linear functionals over C0 of naught are integration with respect to some measure, and if it's multiplicative, it is an exercise to show that it has to be evaluation, like Dirac measure. So these are exactly evaluations at points X, namely the points. How can a sister algebra seize its points? These are the irreducible representations. So maybe we should think about general sister algebras as something that lives above its irreducible representations. Like the irreducible representations will behave as the points, and the sister algebra itself will behave as functions above the points. So if I take pi in, so here of A, just an irreducible representation of A, and I take an A in A, how do I view A as a function over pi? I mean, what does A do to pi? Well, the only thing it can do, right? A of pi is just pi of A. Right? Okay. But I need a topology. If I want it to be something that is analog to compact or locally compact topological space, I need some kind of topology. And indeed, people came with many examples of topologies. The Feld topologies may be the most famous. Never mind right now, but I just wanted to give you a hint to something that happened back then. People were trying to view C-star algebras, even in the non-commutative case, as certain kind of continuous functions over certain kinds of compact or locally compact space. And the point should be, morally, the irreducible representations. Makes sense, right? But people have failed. I mean, so okay, in certain sense they succeed, in certain sense they fail. Right now there isn't, I mean, what is the goal? The goal is that, I don't know, I will be able to begin a course about C-star algebras as follows. Giving you some axioms of a non-commutative topological space, or locally compact, or compact, I don't know, Hausdorff. Example will be a locally compact topological space, right? Give you a definition of continuous functions. Non-commutative one, and then tell you theorem. There's also another definition of like something that I call the C-star algebra that satisfies all the axiom of being Banach space with involution, blah blah blah, satisfying the C-star equality. Theorem: every C-star algebra is of this form, is continuous functions over a non-commutative topological space. We don't have this right now. In certain cases, we do have this. For example, if there is more structure, and we can, I mean, we do have a version of this thing in case that X has more structure and it is convex. So if it has structure of convexity, then I can define something non-commutative that will generalize this. And then I'll be able to define something that will generalize continuous functions over it. And things behave really nicely. And if you want to hear more about these things, come tomorrow. Eli will speak in the Midrasha. So we'll speak about something else, I think, but this will be along the lines. And maybe we will also go to this direction later. Okay, right now, I just wanted to let you know that the goal, I mean, the general goal of C-star algebra in this sense is still open. We don't know how to do it.
Aren't there like good reasons to believe that you can't do it? Just can't.
I don't know. So I don't know if you remember the hierarchy, hierarchy that I showed you in the first class. On the first class, I showed you that there are the C-star algebras, above them von Neumann algebras, below operator systems and operator algebras, and down there operator spaces. For operator systems, there's something that works smoothly, nicely, amazingly. I mean, the theory just works. You can view operator systems like commutative ones, or these are the things we call function systems. We'll discuss about these later. And there's a version like to generalize this from the commutative point of view, and every non-commutative, every operator system is a non-commutative function system. Okay. So this was just, I don't know, nothing for me from here at least. Okay. Now, let's go 20 years before these things, the 40s. So there were two notions that, well, not exactly, but let's say there were two notions, one of abstract C-star algebras. This is what we were defined as a C-star algebra. And the other is of concrete C-star algebra. A concrete C-star algebra is just a star subalgebra closed of B of H. And today we'll show that every abstract sister algebra is in fact a concrete. Okay, so definition. Maybe let me start with something more general a bit, and then linear map between sister algebras. Phi from A to B is positive if it maps positive elements into positive elements. If B, I mean the range is just complex numbers, then B is called positive linear functional. If further the normal phi is 1, then phi is called a state. The set of all the states phi is a state. It's denoted usually by S of A, and it's called the state space. Okay. What else? So examples. What are the states of? I think I said it almost today. What are the states of C of X?
But
What did I forget?
no, it's only super.
Thank you. The Dirac measures. Okay, so from the the name that you're familiar with, every positive linear functional will be integration with respect to a positive measure, regular, Borel, right? And it will be a state if and only if it is a probability measure. Okay, so if and only if phi. Well, I can think of it as a probability measure over X.
Don't you want it to be exactly the other?
Sorry.
No.
No, it's not multiplicative. Phi of F. Some kind of FD. For some reason. Maybe let me write it like this. But I will not distinguish between U and phi. What about Mn? So Mn is Mn of complex numbers, Mn matrices of the complex numbers. Of. So it's something that sometimes people prove in some exercise sheet in a linear algebra, that any linear functional of Mn is of the form. So you take a matrix A in Mn, and then you form a linear functional phi A. Phi of t is just defined to be the trace, the regular trace of AT. So of course, this is a linear functional. It's not how to show that any linear functional is of this form. This gives you an isomorphism between Mn and Mn star in the linear algebra sense. Okay. And who will be the guy that corresponds to states? Any guess?
It's just this representation.
Right, okay. You're right.
Positive matrices?
So positive matrices
No.
with trace functions. So the state, if and only if phi is phi A with a positive definite matrix, which corresponds to positive element of the C-star algebra Mn, right? And trace of A is 1. If you're not convinced, then exercise prove it. Okay.
You can, for every state you can do it, right?
What? What?
If you have a state on a C-star algebra, you can always take a new state by taking an element, positive element, and taking the place of this element times.
If I'm starting with a state, or
You have some C-star algebra A.
yes,
You have some state on A.
yes.
And then for every positive
No, but not
element,
every C-star algebra is trace.
if you have,
If I have a trace,
Yeah.
then I can define.
you can define a state by taking a
Yes.
positive element. And you totally all the state.
So not every C-star algebra is trace also.
Okay.
But let's forget trace. If we have one functional
If I have a functional,
and a positive element, so a new functional, can it be just, what does it do to t? It takes the old functional a times t, like just like
you're saying if I have a
positive-
state, say,
yeah, a state.
a
Yes.
state or a positive linear function, then I can form a new one. But if it's not commutative, then it is not clear that A times B, like if B is positive and A is positive, A times B need not be positive, right? But if it is a trace, then you can think of A times B as A to the half, B, A to the half. You can take 1 square root of A and plug it in into the second place because, why? Because this is a trace. And then, it will be something of the form X star BX, which is positive if B is positive. So you will have a new positive linear function.
So you need a cyclic function.
Yeah, you mean that like trace.
Yeah.
We call it the tracial functionals. Tracial states, yes. So yes, in this way, tracial state gives a way to form new states. Okay. Another example. If can you turn on one of the ACs or? Thanks. I don't know, but not connecting. Okay, never mind. Another example, if pi is a star representation and psi is a cyclic unit vector. I didn't define cyclic, let me define. The unit vector, in that norm is 1. Right? Cyclic means that well, it spends, well, after applying the representation over it, it spends everything. So its orbit is dense.
Is it everything? Not just them?
Well, if things are finely dimensional.
Okay.
So if you take something like this, phi of A to be psi, pi x psi. Okay. this is a state. It's not how to check it is a state, right? Because star representations are in particular positive, and in the sense of Hilbert spaces, it will be positive, right? So, and it will be of norm less than exactly one. So it will be a state. Such a state is called a vector state. Phi, such a phi is called a vector state. And one way I like to think about vector states is as follows. So imagine for a second that pi is finite dimensional. It need not be finite dimensional, but imagine for a second it is a finite dimensional. So pi of a acts on C to the n. So what is pi of the n? Pi of a? Pi of a is just a matrix, right? Big matrix, an n by n matrix. Now, suppose I don't just take an orthonormal basis of C to the n, but I form an orthonormal basis such that psi is the first member of this orthonormal basis. Then what is phi of a? Then phi of a will be exactly, I mean, in this representation of phi of a as a matrix, phi of a will be exactly the 1-1 corner. Right? Do you see it? So it means what? It means that vector states are exactly those states that I can view as a corner of the star representation. Vector states are exactly those states that I can view as a corner, or as a 1-by-1 corner. These are called corners. I mean, even if we take it bigger, then I can call it 4-by-4 corner, something like this, or 17-by-17 corner. But this is a 1-by-1 corner of a star representation. And this is true in a moral sense, even if pi is infinite dimensional, right? Even if it's not a matrix, it's not correct. So today we're going to prove that any state is of this form. This is more or less the GNS.
Why do you need psi to be cyclic?
So you don't have, well, if you assume that, I don't know, that the representation is irreducible, say, you don't need to have the psi cyclic. But in general, I mean, I want...
I mean, it is a state even if it's not irreducible, right?
Irreducibility is that everything is.
Irreducibility, yes, everybody is exactly right. No, but what I want here is that, okay, my main point is that I'm going to show you that any state is of this form. Any state gives rise to an Hilbert space H, a representation pi, and a cyclic vector psi, such that it is satisfy this property. So this is what we're going to show now. So this is called the GNS construction. Maybe let me check if I want to show. Okay, before moving to the GNS construction, let me just state a few things. Remark. Let's call it remark 1 because I know I'm going to have remark 2. If phi is a state and A is self-adjoint, then phi of A has to be in R. Why?
A star, phi of A star.
It's not an homomorphism. States are not star homomorphisms.
Okay.
These are not characters or multiplicative in any way. Why?
You have a B
No,
star
because, yeah, phi of A star is
what?
that's an nature of phi of A.
Why? I didn't assume that, right? Well, I want to convince you that states are self-adjoint in the sense that you just mentioned, but if you show this, then it shows what you said. But why? If it's positive, then right.
And if it's negative.
And if it's and in general, That's fine what he said. So he said that if A is positive, then I get something positive. If it's negative, I get something negative. And if it's a general self-adjoint element, then we can split it into positive minus positive, right? Or positive. We show this a few times. I mean, it's really easy. If the sister algebra is unital, then it's an easy exercise. And if it's not unital, then it's a hard exercise that we showed it. It's continuous function. So y, write A as A plus minus A minus, where A plus A minus are positive.
What do you have in mind?
Both of them are positive. This is the negative part of the.
So why can't you just like minus?
What?
Why did you write plus minus?
No, the plus is a subscript. Yeah.
Okay.
These are subscripts. Like the positive part of A and the negative part of A, and there is something like this. Okay, so 5A will be no. I mean, because this is positive, real. Okay. Awesome. Therefore, I claim that phi is indeed self-adjoint. What do I mean by saying that phi is self-adjoint? I didn't define it, but you know what do I mean by this? I mean that 5A star is 5A bar. Why? Because every element is sum of two self-adjoints, right? Because write A as B plus IC, BC self-adjoint, then phi of A star will be phi of B minus IC. Right, there are stars here, but these are self-adjoint, so I don't care about these little stars. This is just phi B minus I phi C, which is exactly phi A. Okay, so this was one remark. So this is something we got for free from just being positive. Mark 2.
Is there a positive?
Yes,
Oh,
not homomorphism. Star homomorphisms are automatically positive, but here we speak about things that are linear and positive.
Oh.
I don't assume anything else. Yes, and I used only positivity. So this has nothing to do with the fact that I require that the normal field will be less than 1. And remark 2, I can always define something like this. If phi is a state, we can define a sesquilinear form like this. A, B is phi of A star B. So this will be a positive. This is positive sesquilinear form. And in particular, it satisfies Chi-Schwarz. So what is Cauchy-Schwarz? It is AB is less than or equal to square root of AA times the square root of BB, right?
With the norm on the left side.
So these are absolute values. Yes, sorry, thanks. Well, it's true also without it, but so this is nothing but phi of A star B, and this is nothing but square root of phi A star A Let me write it without the right. So the truth, in fact, yes, I wrote it, both of the remarks for states, but they are true for any positive linear functionals. I didn't use the fact that the norm is less than 1, right? So just these are true from any positive linear function. Okay. So I think we're ready to go. No, not yet. Yes, so lemma. Positive linear functionals are bounded with norm that is phi of 1 in the unital case, and limit of approximate identity in general. Okay, so if you think about it for a second, I mean, this is redundant. I could mention only that the second. Because of course, if you're in a unital case, then
lambda converges to 1.
If you have the loop unit and 5, then
so things are tricky. Well, let's check it.
What's E lambda?
So yes, E lambda. Well, E lambda is an approximate identity. So we show that any system algebra has an approximate identity, namely the net that, well, converges to 1. No, it doesn't converge to 1 because we don't have 1, but when you multiply it by another element A from the right or from the left, it converges to this element. And in addition, I can assume that these guys are positive and projections.
Oh, you know it has a limit, 5 to. But you know,
So it's a bounded increasing net
why is it increasing?
because the E lambda is increasing again. Yes, so it's an increase. So proof, unital case. If A is between 0 and 1, then we know by positivity that phi of A is between 0 and phi of 1. So therefore, if A is just with norm less than 1, then phi of A is the usual tree, right? Then phi of A norm square is phi of 1 star A square. This is by the Cauchy-Schwarz equality is less than or equal to phi 1 star 1 phi A star A which is phi of 1 times phi of A star A. But phi of A star A is less than phi of 1, right? Like this. So this is less than phi of 1. So So phi of is A is less than phi of 1. So no need for absolute value. So phi is less than, and phi of 1 is 1. Sorry, and phi of 1 is
You need to assign the norm of value.
phi. What again?
What exactly didn't you assume that phi of A?
No, I'm saying if A is between 0 and 1, then phi of A is between 0 and phi of 1. This is because phi is positive. Now, in general, if A is norm less than 1, then phi of A square is phi of 1 star A square by the Cauchy-Schwarz. This is less than or equal to phi 1 star 1 times phi A star A. And now use the previous case, the positive case, apply on A star A to obtain that it will be less than phi of 1. So this is less than phi of 1, this is less than phi of 1. So it's all less than phi of 1 squared. So I started with an element of norm less than 1, and I showed that the norm of phi is less than phi of 1.
It's special for 1, or if A is phi
So it's what?
It's phi if A is smaller than B, positive.
Yes, of course, because phi is positive. So B minus A is positive, so phi of pi. No, I mean, okay.
But you have to show only for positive elements?
No, I showed it for okay. So maybe I made it. First case for positive element, it's clear. Now in general, if A is just as norm less than 1, then I use the positive case here. And I'm done. Fine? Okay, now the non-unital case. So here, the problem is first to show that phi has to be bounded. I mean, it's non-trivial, but it's not hard to show this. So note that phi is bounded. Let's first show this. Let's first show this on the cone of positive elements. Okay. So let's show that phi is bounded. First on A plus, which is all the positive elements. If not, I can find a sequence of positive elements. So I can say that I can find a sequence of positive elements such that the norm is 1, but 5 of them will be greater than whatever I choose. So instead of doing it like this, I will say that there exists a sequence AN such that phi of AN is 1, but the norm of AN is less than 1 over 2 to the n. I want something that will such that the series AN will converge. Let A be the sum of the ANs. It converges, right? So A is an element. You know, system algebra. So A is clearly greater than the first k elements. Phi of A is greater than phi of this. But phi of this is what? K. So phi of A is greater than phi of the sum which is K, which is, well, yes, K. So this is not possible, right? But of course, I can take any element
Contradiction to what?
to the fact that phi is a function.
Ah, it was 5A for any.
That's right.
Ah,
Over K.
Right, but
You didn't
if
use
it's not positive, I mean, if I take an A that is not positive, then I can decompose it into 4 positive elements. So it's bounded on each of them, so it's bounded, right? So in general, so first on A plus, now for all of A, decompose A and A as a inner combination of 4 positive elements. Fine. Okay, so it's bounded. So now we know that phi is bounded on A. Since E lambda is increasing, phi lambda is an increasing net.
The norm of lambda force is 1.
Yes, phi lambda is increasing and bounded. That M to be the limit. Then, so for any A, phi of A square, which is the limit of phi of E lambda A square. I'm going to use again Schwartz. So this is less than or equal to the limit of phi of E lambda square, right? E lambda is self-adjoint. Phi of A star A. But this guy here is less than or equal to E lambda.
It's not a projection.
Right.
We did-
No, did we assume it's a projection or not? I mean, there are a few versions of this.
But you get it by plugging in E lambda, right?
So, yeah,
No.
I mean, it doesn't matter right now. I mean, just okay.
Yeah, it doesn't.
So this is less than or equal to limit of lambda of phi E lambda, phi A star A, and this is right. This is M. This is M times phi times A star A, which is M times phi times A square. Right, so So what? So the norm of phi square is less than m times the norm of phi. So the norm okay, this is what we want to show. Yeah, so this was just a technical computation, but now we know. So
How did we get to that?
what?
How did we get rid of A? So
How did it get to?
sin A squared is smaller or equal than divide by norm of A squared. We get norm of phi squared in the left.
Divide both sides with the norm.
You can divide the norm both side by this, or you can take supremum over A less than 1 in both sides.
Okay.
This will give you the norm of phi squared. This will give you 1. Okay. So the point is, okay, so forget for a second about the technical details. The point is this. If we start with a positive linear functional, so maybe that's the way I want you to remember this. Corollary, if A is unital and phi is positive, linear functional, right? Then phi is a state if and only if it is unital. And if it is non-unital, then the same thing is true up to taking approximate identity instead of 1. But right, this is what we show. So we show this now, right? We show that the norm of phi is phi of 1. So if phi of 1 is unital, then the norm of this guy will be 1. And of course, so I can take it even equality, of course, right?
Why can't its norm be less than 1?
So no, you're right. I should, yes, I should write this. You're right. You're right. I can take, of course, half times the state. It will be positive. Okay. Now, what?
Now, from this analysis, is it clear yet that every phi extends to its unitization?
No.
Oh, yes, so there is unital.
No, you asked a different question. Not yet.
Not yet.
So, but you did say a few times.
So wait, when I define the state, I mean, it's not really, somebody takes notes. When I define state, I wrote that the norm is less than 1 or equal to 1? Equal to 1. So this is what I want. Now I got frustrated. Sorry. So yeah, so it's a state if and only if, of course, I can always take a state times half. It could be of norm less than 1 still, but you know, functional.
Is it sometimes defined as norm of most one?
What?
Is it sometimes defined the other one?
Yes. So you mean if people sometimes define state like this and then show?
No, you sometimes define that the norm needs to be at most one.
No, it can't. It's wrong to define it with norm at most one because it can always take half of the state,
Okay.
which is a positive linear functional of norm half.
Or 0 will be a state.
Or 0 is a state, yes. I mean, if I define it. Okay, no, so it's with norm equal to. Okay. Once it is unital, then it doesn't matter. So if it's unitary, you can think of it as if it's just less than 1 or equal to 1, it's the same thing. Okay. So later on, I will show you that in fact, if I assume that phi is just linear functional, then, and I take also the property of being positive, then any two of the properties will imply the third. So if you are positive and have no 1, then phi of 1 is 1. If you are positive and phi of 1 is 1, then the norm of phi is 1. But also, if these are two odd, then you have to be positive. And this looks like a magic, I think. So if the norm of the linear function is 1, and phi of 1 is 1, then phi is positive.
And can here you weaken it to being at most 1? I'm just trying to figure out why you made that mistake.
If 1 is 1, if 1 is equal to 1, and the norm of phi is less than or equal to 1, then it is automatically 1, right?
Yeah.
The norm of 1 is 1.
Okay, so you just need to be bounded.
Yes. Okay. GNS presentation or GNS construction. Let me start. So the GNS construction. G for Gelfand and for Nymark, S for Sigma. Gelfand. Nymark. So suppose phi is a state. We will associate to this triple pi phi, h phi, psi phi. Well, pi phi is a star rep from A to your h phi. H phi is the Hilbert space. And psi phi is the cyclic unit vector. I remind you, cyclic means that pi of A in psi phi is dense. So its orbit under representation is dense. Such that phi of A is psi phi, pi phi A, psi phi. So I'm going to give you now a recipe how to do it. The construction as follows. We're going to construct first h phi, then pi phi, then psi phi. Okay. Morally, well, I want you to have in mind the picture of the big matrix and the one-by-one corner that I drew before. And later on in the course, we will see that this is much general phenomenon. Okay? And that positive things are corners of star homomorphisms. But right now, let's do it. So okay. So set AB as before to be phi of A star B, and to be all the A's in A such that phi of A star A is 0. Note that N is also all the A's in A such that phi of B star A is 0 for every B in A. Why is this true in 2 words? Cauchy-Schwarz. Do you see it? Due to the Cauchy-Schwarz, every A in here, for every term of this form, is less than or equal to phi of B star B times phi of A star A. Right? So if A is in N, then A is also literally. And this also tells us that N is left ideal, right? So do you want me to elaborate more on this Cauchy-Schwarz, or is it okay? Right, just because this is less than or equal to this times B star B, and therefore N is left-handed. Why? Because since if I don't know, N in N and A is in A, then why do we have that NA is in N? What would be in A? Phi of B star and A is phi of N star B. No, it's something wrong. I want to show that
Space of it, so then.
it is a left hand. Thank you. And this is phi of A star B star N. Okay, she's it. Since N is in N.
And we use the first definition just to make sure it's closed.
Okay, yes, and also morally, I want this to be like the kernel of the inner product. So I'm going to define by this, and then I know that I modded out all the guys that like I get an honest to God inner product.
It is not the right idea?
No, in general, this is not the right idea. So, but that's fine. So N is left ideal. Let's find it. And it's clear that N is closed. In fact, it's also easy to see from the second definition that it's closed. It's clear also that N is closed. Define an inner product on A mod N by, so let me denote the guys in the quotient with the bar over them, okay? So what? So A times B, inner product with the subscript phi is phi of system. Okay.
And this is the Hilbert. And again.
I need to complete it first. So first you need to verify that this is well defined. Why is it well defined? I mean, if you take another guy, write B prime such that B prime bar is equal to B bar, then of course this will give you the same number because the difference will be in n, right? So this is well defined this function. So now we can complete let h phi be its completion.
N is not star invariant.
Right.
N doesn't have to be star invariant.
N doesn't have to be star invariant.
Like if it is, it's clear. Just
No, I mean, how? Why do?
no.
You wanted to say that if it is star invariant, it's also a right idea.
Yeah, well, I don't see why it's clearly well defined. That's it. But maybe,
Why it's clear that this is well defined?
yeah, on the right hand, if A is A prime.
Okay, let's do it.
So
Let's check.
okay.
This is well defined.
Switching B to B prime, that's by definition. Switching A to A prime needs other direction.
But you remember that phi is self-adjoint,
Phi is self-adjoint. So
right?
okay, so phi is self-adjoint.
So I mean the fact that this is a sesquilinear form has to do with this. Okay. So by the way, just a note to yourself, later on I will say something about it. If we start with A separable, then can I say anything about H5 right now? That it has to be separable too? Yes, I can. Yes. Right? Because I completed the quotient of A. So of course there are different topologies, but if you think of it, if you start with a dense countable set in A, you get a dense countable set in H5. So that just put it in the back of your mind. Say something about it.
Can you give an example of a vector in the completion that is not in the quotient space?
The vector in N?
No, the vector is the completion of
In the completion.
In the completion, you want an exact. So, okay, I can tell you a secret, but yes.
If you want to use.
So this guy. Okay, we didn't speak about. We haven't mentioned yet pure states. For pure states, this space will automatically be complete, so you don't need to complete it. So pure states are going to be the extreme points in the state space of A. I'm going to discuss about this. But for things that are not pure, you can give examples that this will not be complete. It's not how to manufacture an example, to produce an example that satisfies this. That's it. Is the exercise. Once I told you what is the abstraction, being pure, construct something that will mess it up. Okay. But yes, I just want to finish with construction. So let me define pi phi. So, well, I'm going to do the only thing possible to define. For every A in A, and for every B bar in. So first I'm going just to define it on the quotient, and then I will say that I can extend it in to the completion. Pi phi A of B is AB bar. Don't get confused. These guys are vectors.
Bar is the function from A to A mod n.
Yes, bar is the quotient there. Okay, so now we think of these guys as vectors somehow, and so this is well defined. Why?
Because the action portion.
I mean, if you take another B, why do you, right? If you take here B prime, that such that B bar is equal to B prime bar, then the difference, second guy, I mean, the difference will be of the form A times something in the ideal, but this is a left ideal, so everything will be in the ideal. So all the bar of it will be 0. Okay, so check the details if it's not clear. So this is well defined since n is left ideal and left ideal.
The natural to multiply from the right to left.
No, it's good, right? I'll get here. So I take the difference, B minus B prime, and then I get it A times B minus B prime. B minus B prime will belong to n. And here I have a product, something that left multiple. Yes. Yes, it happens sometimes. Pi n from A to n to A to n is clearly linear. Is clearly linear. And it's also bounded, it's more than that. Pi phi of A of B square is pi phi over AB, pi phi over AB. Which is right AB bar B phi, and this is nothing but phi of AB star AB, which is phi of B star A star A B, which is less than or equal to A star A times phi B star B. Right here, I only use the fact that A star A is less than its norm, plus the putting B star B from both sides, something we did before.
With phi effect.
But this is no, just
We may tell you.
It is positive.
Times 1.
it's times 1 if you. So, and this is nothing but A square B, right? So this is like A square B square in H phi. So pi phi of A is a contraction. So it extends to its closure. It's continuous and it extends to its closure. So pi phi extends into pi phi of A extends into pi phi of A into H phi. Okay.
Can you repeat how the A star A got out with the norm?
Yes. So is this fine?
Yeah. Ah, of course. Okay. Thank you.
Thank you.
Yeah, it was. Yeah. Mhm.
Okay. So taking something positive and multiply it from the left and right by B star and B preserves its positivity. So also if there is another one, the positivity is just subtracting one of the others. It's nothing but, and if A is less than B, then C star A C is less than C star BC. This is something we did last time, I think, a few times. Okay, now I owe you the vector. Before the vector, let's verify it as a presentation.
The norm of pi of A is the norm of A.
Yes. So the map. No, sorry. We just said that the norm of pi of A is less than the norm of A. I didn't show it. In general, you need to know something about phi. Okay. The map pi phi is from A to B of H phi, and it's clearly linear and multiplicative. Linear and multiplicative. This just follows from definition. It's not clear that it is self-adjoint, however. Okay, so let's verify. That phi of A star is phi of A. So let's do it on vectors. A star. Yes, Dan?
It's also contraction.
Yes, it's also a contraction. So let B and C be and N. Then let's check what is phi A star. This. So this is what? This is just being in a product with A star C, like this, right? This is phi of B star A star C, which is phi of AB star C, which is AB bar C bar, which is phi of AB bar C bar, which is B bar phi of A star C bar. So this is to some completion. Okay, let's define psi phi and then we take a break. Defining psi phi. If A is unitary, then take psi phi to be one of the unit of A, bar. So psi phi times pi A of psi phi this would be just 1 bar A1 bar, which is pi of A. If not, now that's the part of Sega, I think. If not, let E lambda be approximate identity. Then E lambda bar is Cauchy, is a Cauchy net. Of course, E lambda is not a Cauchy. Why? How do we know that E lambda is not a Cauchy? Right, because if E lambda is a Cauchy, then it converges, and then right it is complete. Then it has to converge the identity, but there is no identity. No, it's not a Cauchy, but it's Cauchy in H phi. It's a Cauchy net in H phi. Okay, maybe let's show this after the break. We'll show it. I'll show it. Okay. And then that's psi phi. Its limit then psi phi pi psi phi would be the limit of E lambda bar pi A E lambda, which would be the limit of phi of E lambda A E lambda. Which will be okay. So we are done with the GNF modulo to show that E lambda is a Cauchy net. Show it up. Yeah.
משתדל מההרצאה השלישית. יש לך קבוצה שלך?
קבוצה.
יש קבוצה.
כן.
אני עכשיו מנהל, כן. למה אין כפתור להפוך את כולם למנהלים בבת אחת? כן.
עוד מעט עוזבים כסיסטם.
אז את תלונות לזה. לגיא.
יש גם דרייב.
מי זה? מה שם? אורי. אורי,
זה אתה? אז אתה התחלת עם...
אתה הכותב המהולל מהשיעור הראשון?
מהשיעור הראשון. נכון, גם שלח.
ועכשיו גם כתבת? לא.
לא. תחילת סמסטר, היה לו מוטיבציה, עכשיו די. מה, קיים? אתה עוד כותב? אתה מעדכן? חבר'ה, זה היה ידוע למישהו?
עכשיו אני רואה.
אתה צריך לשלוח מיילים בתפוצה.
קודם כל שאלה רבה.
אז אתה אומר שבמכפלה הפנימית שלא חייב לצאת שלם. אז זה אומר שהנורמה של המכפלה הפנימית זה לא אותה נורמה שאני מקבל כמאפשר.
וואלה, זה 23 עמודים, חבר'ה.
יש מקרים שזה כן נכון או שפשוט אין קשר?
או, חוץ מהמקרה הסוף ממדי שאולי זה...
הופה, וואטסו, טופולוגי, טבלאות.
בוא נתחיל מזה שאין מודל מחר.
לא, אנחנו לא מוסיפים לך, מה המספר?
0509
כן.
115 199.
ותזכיר לי את השם?
כן. אוקיי, אז הדוגמה הזאת בפרט היא צריכה להיות דוגמה שבה מלכתחילה הנורמה שלו מגיעה מסוג של פרודקט.
כן.
לא, כן, ומצד שני גם צריכה להיות נורמה כזאת סוג של נורמת בנה, של לא כל. איזה נורמות מתקיימות גם נורמה של אידית, של נורמה יום מלווים,
אבל זה לא, זה כבר לא צריך לקיים, זה לא, הכפל כבר מוגדר במדע.
אז לא, אבל מכיוון שהתחלנו בסיסטם אלגברה, לא צריך לקיים את זה למעלה. מצד שני, הנורמה במנה צריכה
איפה הלינק בדרייב, אולי כדאי
אתה אומר אולי נתחיל
עכשיו תראה, אני משדרג גם אותך לזה. אתה עכשיו תהיה במעמד מנהל.
נכון, אז יכול כך אתה
כן, אולי אפילו אם היה פה מנהל בכיר, הייתי גם שם לך מנהל בכיר.
במקרה מה שצריך לסוף נרדי, ואז אני אומר, אז איזשהו מסכים, צורך אולי.
ברעיונות עבודה אני אגיד שיש לי ניסיון.
בתור מנהל בכיר אבל. לא עכשיו יש לו מנהל זוטר של איזה פתיחה.
גיא, עכשיו תעשה את זה על כל סטייטים. רגע.
Yes, Aviv asked a good question in the Zoom. Maybe I'll repeat it for everyone. מה השאלה?
שעכשיו אתה תעשה פשוט, כאילו ה-H שלנו, זה פשוט יהיה סכום של כולם.
אני קודם כל רוצה להצדיק את זה, שיש בזה טעם בכלל, כלומר, מה שקיים, שבעצם אני אקלע ככה להצגות. אוקיי, אני רוצה בסופו של דבר לשכן את פייסבוק. לא רוצה סתם לרוץ להצגות, אני רוצה להצגות לא, אני בא לרוץ.
סליחה, עדיין ספליץ.
אני אומר אפילו בסטייטים, אבל אני רוצה לדעת שאני יכול לתפוס שזה יהיה פייסבוק, כלומר, אני צריך להיות הפרט צריך להיות איזומטרי, כלומר אני רוצה לדעת שאני אתפוס שם פיים, כך שפיים שלי זה הנורמה שלי. זה לא הורג משהו בדיוק. ובעצם מה שאנחנו צריכים להצדיק זה שלכל דבר אני יכול למצוא state. קצת פחות מזה, מספיק כאילו לבד כאילו קצת יותר מזה, מספיק למצוא state שפי, כאילו פי, כך שפי של האיבר הזה היא הנורמה של האיבר הזה. סוג של ההנבנה אחר.
גיא, אתה יכול להזכיר את המטרה הכללית? אני קצת נכנסתי לפרטים.
זה בסדר, זה אין מה לעשות, ידעתי, אין פה הרבה ברירות. כרגע בנינו מכל סטייט
את המרחב עם ההצגה עם הוקטור הציב.
יפה. אנחנו עכשיו נגיד שני דברים. קודם כל, נדבר רגע על הבנייה הזאת, נתידה להם משהו. הבנייה הזאת היא לכשעצמה משפט מעניין. כי המשפט היא אומרת, תשמע, כל סטייט בעולם...
תביא הצגה איתו.
לא. כל סטייט בעולם הוא מגיע כ-contraction של representation כזאת. לא contraction, כ-compression של representation כזאת, כ-one corner כזה. אתה לא יכול, זאת אומרת, אם אתה יודע, כאילו, נכון הרי, והדבר הזה יהיה טיפה יותר כללי, בהמשך אנחנו נגיד שכל העתקה חיובית לחלוטין של משהו טיפה יותר כללי, זה היא כזאת.
אז זה גם קצת מזכיר תורת ההצגות, וזה שבתורת ההצגות אתה יודע את הקרקטר, אז אתה כבר יודע, זה כבר מסווג לך את ההצגה, אז פה אתה יודע את הקורנר, זה מסווג לך את כל, גם כן את כל ההצגה.
לא בדיוק, כרגע אנחנו דווקא בכיוון, כרגע אנחנו בכיוון שכל ההצגות אומרות עם הסטייגים. עכשיו פניו זה אולי לא מרשים, וזה מאוד מרשים.
אוקיי.
אוקיי, ההצגות אומרות עם הסטייגים. כרגע מה שאומרים, שזה עצמו מרשים. אחרי אנחנו נגיד ש...
אבל פה בנינו מסטייט הצגה.
נכון, ולכן אם אתה מכיר את כל ההצגות שלנו בציג כוכב, אתה גם מכיר את כל הסטייטים. אין סטייטים אחרים. לא, את ההפוך לא בדיוק.
ההפוך אנחנו לא...
אמרתי רק דבר אחר. אמרתי אם אתה מכיר את כל הסטייטים, אתה יכול לבנות להם הצגות. לא אמרתי שאתה קולע כך לכל הצגה או משהו כזה. נכון? אני לא נותן שכל פייפ פי של איזשהו. אבל...
גם לא הכל רדיוסיבל?
לא, אני לא רוצה שזה אני חושב על זה ביחד. אבל... המטרה שלי עכשיו תהיה אחרת. המטרה שלי תהיה להראות שבעצם אני יכול faithfully ליצור הצגה שהיא ליגרית, שהיא זומטרית, בעצם לשכן את האלגברה ציג כוכב בתוך איזשהו BOH באופן ליגרי. ואז בעצם אני יכול להגיד שכל האלגברה ציג כוכב היא זומטרית לסטר איזומורפית באלגברה ציג כוכב קונקרטית. תת אלגברה ציג כוכב של BOH. וזה נעשה בזכות הג'ניוס, כי אני אבוא ואני ארוץ על כל הסטייטים, אני אקח סכום ישר כזה לכולם, ואני אצטרך להראות לכם למה זה נאמן. ואנחנו נשחרר גם את הבנייה הזאת וגם את מה שהיא נותנת לנו בהמשך, גם בשבוע הבא וגם בהמשך. כן.
לפני שאתה מתחיל פונקציה.
מה זה?
זה טייוואן.
יש לי איזו שאלה כללית כזאת, כאילו, אני ציפיתי שכאילו הוקטורים במרחב הילברט הם יהיו מצבים מבחינה קוונטית, אני מכיר. אז אתה מגיע עם הדברים האלה, זה משהו אחר. אז איך אני איך אני מוצא פה אנלוגיה למכניקה, מה שאני מכיר למכניקה קוונטית?
אוקיי, לא אני חושב
כן, אבל כאילו אבל גם המצבים התיאוריים פה הם לא אלמנטים בהילברט ספייס.
זה אנלוג של לקחת אופרטור כאילו שמייצג קוד אלמנטי, ואז
לקחת את החלק של איזשהו מצב פי, כאילו נכון שיש לך את ה... אתה מכפיל אותו מימין ומשמאל.
כן, אני יכול לחשוב כאילו על התוחלת של כל, כאילו לקחת מצב ולחשוב על התוחלת של כל אופרטור ולחשוב עליו בתור כאילו פונקציונל על אופרטור. אז מרגיש קצת כזה, בכל הפוך.
אוקיי, אני לא יודע למה אתה אומר ש-GNS אמורה לי את הדבר הזה, בעצם
GNS?
כאילו, אתה אומר...
לא, כאילו זה רמת הסטייט.
לא, יש סטייטים ויש פיור סטייטס, אנחנו מדברים גם עליהם תכף.
אני חושב שזה טרמינולוגיה מקוונטית.
טרמינולוגיה מקוונטית, מה התפקיד שלך? תסביר לי ואז אולי אני אנסה...
שמצב זה כאילו... מצב.
זה לא מה שאתם רושמים בצד שמאל, זה לא כזה ברע, אני יודע.
מצב...
אז בפרט זה פונקציונלי, זה עובד על...
כן.
אבל בפיזיקה קוונטית, וקטור במרחב הילברט מנורמל הוא בעצמו נחשב סטייט.
אני חושב שהווקטור במרחב הילברט שנחשב לסטייט, זה בדיוק הווקטור סטייט יוצא. כלומר, נכון, דיברתי, הדוגמה הראשונה הייתה, הדוגמה השלישית הייתה של סטייט, היום נתתי שלוש דוגמאות. דוגמה אחת במקרה של C of X, דוגמה שנייה במקרה של MN. דוגמה שלישית אמרתי, אם יש לך הצגה, קח איזשהו cyclic unit vector xi, ותכריז את phi a להיות xi, פסיק phi a xi, זה נקרא vector state. ואז המשפט GNS אומר לנו שכל state הוא vector state. אני חושב...
כאילו xi זה המצב.
בדיוק.
כמו שהבנתי.
בדיוק. זה בעצם, אם אתה רוצה לחשוב על זה כמו טנזורון כזה קטן של psi טנזור psi סטאר כזה. one rank operator, לא יודע, אתה לא יודע איך לקרוא לזה. אבל נכון, אני לא יודע, שאתה מקריס אותו על קסאי ואז אתה מסתכל על משהו, אתה יודע שאתה...
אז למה באמת יש הצד שהוא יציג משם בהגדרה?
לא חייב, בדוגמה הזאת אמרתי שאני לא חייב שהוא יציג. אני אמרתי, אני פשוט אפרט לכם שכל אחד כזה, אני יכול בסופו של דבר לעשות שוץ.
כן, שיש פה כזה.
יאללה, יש מישהו שצריך לבוא? אלון, לא משנה, עוד מישהו?
היה פה שיבי קודם, אולי לא נרגיש.
גמרתי אותם. אוקיי. יופי, כאן סיימנו את החלק ה... זה, אז אני חייב לכם את הסיפור על proof that it is a Cauchy sequence, and then I'll have many things to say. Okay. So, proof that E lambda is in Cauchy net in H. So given epsilon greater than 0, of course there is a lambda naught such that for every lambda greater than lambda naught, phi of lambda is greater than 1 minus epsilon. Phi because it's approximate 1 and phi is state, so of course I can do it simply about it. So, and also, there is mu naught. So now I fix this lambda. Also, there is mu naught such that for every mu greater than mu naught, E lambda naught minus E lambda naught is less than epsilon. Okay, so here I fix lambda naught. And now saying this mu. So for any such mu, namely greater than or equal to mu naught, let's compute. E mu minus E lambda naught, well, this is E mu minus E lambda naught E mu minus E lambda naught. This is equal to phi of E mu minus E lambda naught square. So this is phi E mu square plus phi E lambda square minus phi E mu E lambda naught minus phi, or maybe let me have plus and put it in bracket there. This E lambda naught. Okay. Now let's approximate things. So this is approximately 1. Also this guy. I mean, okay. Even I'm going to use the fact that they're less than or equal to 1. I can really do. Now, this guy here is close to E lambda naught. Is epsilon close to E lambda naught? And this is 2 because I can apply star on this. So what? So this is like up to epsilon. Okay, so all this up to epsilon is phi is 2 phi E lambda. So this is less than or equal to, and now it's officially less than or equal to 2 1 minus right, but before that, phi E lambda naught is 1 minus epsilon. Is greater than 1 minus epsilon, right? So this will be less than 2 minus 2 times 1 minus epsilon. So, but I have also the epsilon here and the epsilon there. Okay, so let's do it carefully. So this is 2 minus epsilon is 4 epsilon, something like this. Yes, this is true. This is 4 epsilon. So the thing is, okay, sorry. This was correct up to 2 epsilon. Of course, it's not that important. This is correct up to 2 epsilon, and this is true up to epsilon, but I will 2. And when I say up to, I mean at the end it will be less than or equal to this minus 4 epsilon. Thank you. Okay. Okay. Now, corollary from and by the way, something that we didn't check before, and Aviv asked in the Zoom, on Zoom, and it worth mentioning. Did they show that psi phi is cyclic? I didn't, but it's written there. I mean, just read it and you find out that in fact, from the definition, we know that it's cyclic. The definition of phi. So verify that you understand it's cyclic. Okay, now, corollary. For every phi states, right, there is pi. Oh, there is pi h psi such that pi from a to b of h star psi unit cyclic vector and phi is psi phi xi. Okay, this is what we showed. I just want to speak about uniqueness for a second. If pi prime, h prime, psi prime is another such triple, then there is a unitary from h prime to h there, such that so by A. So if I plug here U takes me from H prime to H to pi A, then I go left to star. This will be pi prime. Okay, so any such two representations will be the same up to unitary equivalence. So we say maybe just okay. With this and maybe of course U of psi prime is psi. Any two in this case we say pi h psi and pi prime h prime psi prime are unitary equivalents. Equivalent. This is a unitary equivalence. Okay. So both existence by the GNS. So in some sense, what I try to show now is that the GNS construction is unique up to something. Okay. And this is clear. Why this is clear? Well, I mean, you define it like this. I write this is cyclic. So I just tell you, U of psi prime needs to be psi. And for me, there is only one way I can define U on pi A, pi prime A psi prime. I want it to be pi A psi. If everything works fine, then I can extend this to the closures, and the closures are H prime and H. But everything will work fine because of this identity somehow. Okay, so it is just a chain of inequality of equalities that one needs to check. So I wonder if we should do it or not.
The only degree of freedom by in the definition of pi, that's in the construction.
No, I'm not going to go back to the construction. That's the idea. Forget about it. I could have done this before seeing the GNS construction. I give you two such triples. I don't know. Two such triples. I'm saying just because both of them would satisfy this, right? They will equal to phi over A. And because psi is cyclic, so pi prime A of psi prime is dense in A prime, and same goes for this guy. There is only one way to define this U and to check that it is isometric and extends, in fact, to a unitary. Okay, maybe I will do it. For uniqueness, define. Yes, it's not exactly uniqueness. Uniqueness of unitary equivalence. Define U from pi prime A psi prime to pi A psi by U of pi A psi prime is pi A psi. Of course, we need to check that U is well defined, right? But it will be well defined. check that U is well defined and isometric. So you can do it in one time. You can say something like this. U of pi prime A psi prime norm square is phi A psi by definition norm square, which is phi A psi in H, which is psi pi A star A psi in H, it's phi of A star A, which is also psi prime, phi prime A star. You see that H prime, which is phi prime of A psi prime square. So U of this guy, right? U of this guy is the norm of this guy. So we see that U is well defined, right? Because if this is 0, then this is 0. So it is well defined. And it is isometric. So I can extend it into an honest to God isometric from the closure of this to the closure of this. So U is isometric, hence extends to U from H prime to H, right? Because H is the closure of pi psi prime, and this is the closure of pi psi. Here we use the fact that psi prime are cyclic, and same and clearly U star is the map that maps right is the inverse. So so similarly it's isometric. So using the U star U is the identity of one inverse space, and U star is the identity of the other inverse space. Okay. Questions? Am I going too fast today, or is it okay? Feel free to let me know to stop me with questions. Okay. Now, so okay, I want to get right away to the conclusion of this somehow. So let me mention a quick lemma. I prove it afterwards, and okay. So and then I'll be able to go right away to wherever I want. So if phi is just a linear functional, this is something I mentioned before, and the norm of phi is less than or equal to 1. And phi of E lambda converges to 1 for some approximate identity. So this in the unital case is equivalent to say that phi of 1 is 1. Okay. If phi is unital, this is just another way to say that phi of 1 is 1. Then phi is a state, and phi is positive. Then phi is a state. So this is just what I said before. I mean, in the unital case, so corollary phase unital and by the linear functional, then two of the following implies the third. One is positive. Two is not one. Three is unital. And if it is not unital, then I can replace this requirement by this one. Right? Because we already proved that if it is positive and three, if we have 1 and 3, we prove 2. If we have 1 and 2, then clearly we have 3. And now we will, this time we will show that if we have 2 and 3, then we also have 1. And in the non-unital case, I also have this, just need to replace 3 of 1 is equal to 1 by this. So now, I prove the lemma in later. I just want to conclude something. Lemma. Okay, so proof later. Lemma for any self-adjoint in A, there is a state such that the state gives us the normal V. Okay? This together with so I will prove it because this is kind of easy. And this together with the GNS construction will give us the so-called Gelfand-9 representations. Okay, so a proof of the lemma. Right, I just want to show that I have a state that satisfies this. So I can assume A is unital. Why? If A is non-unital, then do this on its one-point unitization, and then restrict the state to a linear functional on A, and it will remain a state. So to prove, we may assume A is unital. So C star of 1A is isomorphic to the continuous functions over the spectrum of A. Right, and I have this correspondence that A corresponds to the identity function. It goes to X here. Right, and sigma of A is minus A here, where at least one of the edges belong to the spectrum, and at least one of plus minus norm of A belongs to spectrum. So assume without the loss of generality, this is plus A. That's the norm of A. right? So let's call for a second this isomorphism phi. So I can take, there is one state I know in this guy, and this is the evaluation point on this. This is a point in the spectrum. I can take the evaluation on this, and this is the state on continuous functions over this set. So this corresponds to a state on this guy. So let phi theta 1a star in the dual space be defined by phi of b. I want it to be, we'll take b here, you get a function, now take the evaluation of this function at the point plus norm of a. Just absorb the state from here to here. So it is a state. So phi of a will just be the evaluation, right? Capital phi of a is nothing but the function x goes to x, the identity function. So its evaluation is just the normal way. So phi of a is the normal way. And of course, phi is a state. And now, why can I extend the state in the small sister algebra to the big one? Why? So because of this, I mean, it's easy. So, right, if I know, right, Banach doesn't tell us that we can extend positive functionals to positive functionals, but it does tell us that we can extend positive functionals, functionals to functionals that in a way that preserves the norm. In particular, due to the fact that 2 and 3 implies also 1, I know that Banach tells me, in fact, that I can extend positive functionals to positive functions. So in view of the previous lemma, in view of the previous lemma, can extend phi to phi in a star such that phi is equal to 1. No, not in view of the previous step. So, due to Banach, can extend phi to phi also equal in a star such that phi is equal to 1. In particular, phi of 1 is 1. So phi is a state on A. And clearly, because this was just an extension, phi of A is the normal way.
The fact that phi 1 is 1 is follows from the definition. It can follow from the definition of phi.
Right.
Okay.
Maybe I want to do this on the whiteboard. Okay. Corollary. For any A in A, there is star representation phi from A to B of H such that phi of A is equal to the norm of A. Proof. Pick a state.
Norm of pi of A is equal to the norm of A?
Yes, sorry. Thank you. Take a state phi such that phi of A star A is the norm of A star A. Then phi of A, phi I mean the GNS representation squared is equal to psi phi no, maybe that's stages phi of A psi phi of A psi phi, which is equal to psi phi star A psi phi, but this is just phi of A star A. Is A star A. I mean, for positive things, of course, it will be positive. State, then this is A. Okay. And last corollary, which is sometimes called the Gelfand-Nymark theorem. Any C-star algebra. Okay, any C-star algebra has a faithful, I didn't define the word faithful officially, I mean, wait a second, faithful and star representation. That is a star. Now, but I do want to remind you that one-to-one star homomorphisms are in particular isometric. So it's more than that. Sometimes you will see this theorem rephrased like this. In some groups, an abstract sister algebra, our sister algebra, it's called abstract sister algebra, closed subalgebra, star subalgebra. B of H is called a concrete sister algebra. And then the theorem says any abstract sister algebra is isometrically star isomorphic into a concrete one. which is also a terminology you might see.
So in this category of star algebras, isometrically star isomorphic, we can say simply is, I mean, this
Isomorphic.
Is all the information.
Yes, exactly. I mean, you don't even need to mention isometric. Because if you are one-to-one, then you are automatically isometric. But there is a theory hiding there. And a priori, probably you would want also to carry the norm with you, because the norm is a part of the definition of the C-star algebra. So it is natural to remind it is isometric, categorically speaking. Okay, so proof of the corollary. What's the proof? Take the direct sum. So I didn't define direct sum of representation. Let's do it for a second. What's the direct sum of two representation?
Direct sum of the two Hilbert spaces. And
before the proof, yes. So remark if phi and tau from A to B of H of star if phi alpha from A to B of H alpha star alpha some index at A, then we can define phi alpha direct sum from A to B of. So it will land in the beginning in the direct sum of the B of H alphas, but this is of course sits inside B of direct sum of the H alphas.
And this is why it's just a subalgebra of B of H.
Yes, right. This, like, do you understand this? I mean, so you can think of it as some kind of block diagonals inside B of the direct sum. B of the direct sum is bigger. This is just blocks.
Yeah, you take all the elements in A or only the self-adjoint?
I didn't say anything. I just said something about sums of.
Okay.
I mean, by alpha of A is, well, direct sum of operators is something busy, right?
Why do you take the indices to be the algebra?
No, oh, sorry, it's not an algebra. Oh, thanks. So
That's not simple.
Okay. Proof of the corollary. Let I be the sum. So we said before that any state, that any element, that for any positive element A, there is a state that will give me a representation such that phi of A will be the norm of A. So I can run only over the guys that I chose before. Oh, on all of them. Why do I care? So phi a state of A, phi phi, right, from A to B of H phi, where I run over all the state space. By the previous lemma, למה? למה אין קורולרי? This star F. So this phase. Right, it's 1-to-1. It can't kill anybody. Because for any A, there is a state phi that gives me the norm of A. Well, not exactly. For any positive A or self-adjoint A, there is phi that gives me that, but for the star representation phi that corresponds to this phi, it will recover even like for the A star A. Okay, so we need to collect the details from before, but this is faithful. Just one thing I would like to mention is that this specific representation, when I run over all states of A, this is sometimes called the universal representation of A. So just terminology. This phi is sometimes called the universal representation of A. And since we already defined phenomenal algebras last week, I will also say that so if I have this representation, I can take the double commutant of pi phi of A here. This is a phenomenal algebra. This is sometimes called the enveloping phenomenal algebra of A. Okay, so I'm just mentioning it. And for this specific pi, I mean, if you take different pi, then you might get something different things. So for this specific pi, and pi of A prime is called the enveloping phenomenon algebra. But this was just a remark. Maybe I will use it later in the course, and then I will remind you that we mentioned this once. Okay. Okay. So now, do you have questions? And then I want to prove this lemma, and then maybe we're good to go.
And what can you do this when H is? I mean, this isn't going to be a separable Hilbert space, right? Generic.
Okay. So
can you, if A is small, you will expect this to.
Thank you. This was something I wanted to mention. Let me mention this too. A remark. If A is separable, right, and this is H. Oh, okay, not this one. I mean, yes, this H. If A is separable, we can faithfully represent it inside or on a separable Hilbert space. Why? So, okay, not in this representation, but I'm just saying, if I start with a separable A, then I'm just saying that, in fact, here in the faithful representation, right, I do some, in this term, I didn't commit it on this representation. This was just an example. And on the way, I told you that this example has a special name. But I could do something that is more chesroni. I could say something like, so suppose I can take a dense set, even if it's not separable, but if it's separable, I can take a countable dense set in A. Then I can take only states that give me the norm in this for this countable set, let's say of positive element, let's say that it is dense in the positive cone. So take a countable. So this will be a countable direct sum. I won't run over all states. I will run over the state that corresponds to dense subsets of positive elements that I can take countable and say is countable. So all of these will be countable. But you remember that I told you before that each H phi is the completion of A mod n and is therefore separable as well, if A is separable. So this direct sum will be direct sum of a countable set of separable Hilbert spaces. So it will be a separable Hilbert space. So why? We can choose a countable dense subset of positive elements A, and then a countable set of states corresponding to them. The direct sum of the corresponding GNSs would be separable, or will be a countable direct sum, will be a countable direct sum, and each of the H phi will be separable itself. So thanks, Michael, for the question. I wanted to mention this.
Thank you.
What?
If I just take the cyclic vector in each one and then fix it, then look at the map by alpha from A to H, fixing the cyclic vector. I can choose separability. I can communicate this match to obtain separability.
Wait, what? Again, say it again.
If I fix a separable
AN here.
In H5,
yes.
I pick someone separate in each H5. And someone is cyclic.
Okay, sci-fi in each.
Sci-fi.
Yes.
And then I have a map from A to H5. So this one of H5. The closure of this map won't be everything.
You're saying since, okay, now I understand your question. You're saying since I have I can map each A to phi A direct sum of psi phi. So if I start with a counter, yes, I think it's the same, more or less the same. Yes. Yes. Yeah, I think this would be okay. So I just want to prove the lemma and then we can go on. So proof of the lemma. Now maybe let me just mention that next time. So next time it's Hanukkah. I don't know if there is a on Sunday class. I need to check it. Anyway, please go over the homework, and there is a question there about pure states, even about convex sets. The last question. Please at least read it because I will use its results. I mean the last. I mean, this question is about some kind of modification of what we did today for pure states instead of states. So pure states are the extreme points in the cone of in the convex set of states. I ask you to prove it's a convex set and blah blah blah. So we have all the details in this exercise. Is the last one. Please do it because next time I will want to use the result. Or if you don't do it, at least read it. Okay. Proof of the lemma. This lemma is highly non-trivial. I mean, for me, it was a big surprise to see it, right? If phi has a norm less than or equal to 1, and I don't care, and if phi of 1 is equal to 1, then it's positive. What? How come? If it's contractive and unital, it has to be positive. By the way, this is much more general. So there is a theorem, we didn't define it, what are completely contractive map, but any unital completely contractive map is unital completely positive, which is very weird. Okay. And indeed, I mean, if A is non-unital, the point here is not with the non-unital case. You can extend it to the unital case. So okay, maybe that's right. If A is non-unital, extend phi to phi plus on A plus, the one for utilization, such that phi plus norm is less than 1, is equal to 1. So you can do it because you can, right? You can extend it such that the norm is less than 1 by Han Banach, but also you can also define it to be 1 on 1 if you want. So, wait. No, sorry. I can. So what do I want to say?
If the norm of phi of
no. So you can. No, maybe you. So sorry. If the norm is less than or equal to 1, I can extend it to a norm less than or equal to 1. But because of this requirement,
the norm is 1.
I know that the norm is 1. Yes, but I still don't know that phi plus of 1 is 1. This is something I will show. So I can do it in view of this requirement. Let's show that phi plus 1, let's give it a name, alpha, which is equal to phi plus of 1, it's 1. And clearly, alpha in absolute value is less than or equal to 1. So for any lambda, 2e lambda minus 1, right? I mean, the spectrum of e lambda is in 0, 1. So the spectrum of 2e lambda minus 1 is in minus 1, 1. So 2e lambda minus 1 is norm less than 1. But this means that okay, 1 is greater than or equal to 2e lambda. Sorry, 2 phi of 2e lambda minus 1, which is 2 phi lambda minus phi plus 1. Which is 2 phi lambda minus alpha. But this converges to 2 minus alpha, because phi lambda converges to 1. So 2 minus alpha is less than or equal to 1. So alpha is greater than or equal to 1, right? But alpha, well, yes, I should have done something.
Yeah.
So, well,
Yeah, this is
from here and here, alpha is 1. So this is one thing I wanted to show. So now we may assume, A is unitary and phi of 1 is 1. We need to show that if A is positive, then phi of A is positive. Now I'm claiming that once we know that phi maps self-adjoint elements to self-adjoint elements, well, to the real numbers, we are more or less done. Why? It's enough to show that phi of A star is phi of A bar. Since then, for any A between 0, A greater than 0 with norm less than 1, 2A minus 1 will have norm less than 1 because of spectrum issue like these. So phi of it, since it is self-adjoint, and contractive, it would be, it will satisfy, I mean, since it satisfies this thing, it must be self-adjoint, and we know that it is contractive. So this is what we get. But this tells us that phi of A is between 0 and 1. So if you assume that A is between 0 and 1, then phi of A is between 0 and 1. In particular, if A is positive without loss of generality, you can assume it's less than or equal to 1, then phi of A is positive. So the only thing we need to show is this. And this is difficult. But very difficult, but it requires a trick. I'll give it a trick. So claim phi of A star is phi of A, or equivalently or plane A, or equivalently phi of A within R for every self-adjoint. So proof, if A is self-adjoint, then for every T in R, A plus IT square is A square plus IT square plus T square. So this is just a continuous functional calculus. F of the x equals to x plus I. So you can do the figures. Since phi has norm less than 1, we have that phi of A plus IT is less than or equal to the norm of this guy, which is the square root of the norm of A square plus T square. But this also equals to FA plus IT plus I T, right? Because phi of T is T. So phi of A is in the disk. So phi of A is in the disk with radius. This is Z minus IT is less than or equal to the square root of A squared plus T squared. Now we're done. Why? I just need to draw a picture and you see. What is this disk? That's the point minus IT. PA is in some disk around this point, right? This is the radius of the disk. So it is the square root of A squared plus T squared, but this is T. So this means that this is the norm of A. So this point here has to be the norm of A. And this one similarly will be the norm of minus A. And this is independent of T. So phi, let's call this disk, I don't know, call it DT, okay? DTA. So phi of A is in the intersection of all DTA, of all T now. But what is this intersection? Running over all T, go up and down. You'll see that the only thing that remains in the intersection is this interval. Think about it for a second or imagine it in your head. Okay? So this is minus A. And now we're done. So sorry for taking your time. Which is an hour. Yes. So next time we will do just a quick cosmetic. I'll speak about pure states to tell you what the genus corresponding to pure states. This will be very easy. And then I think we will start speaking about non-self-adjoint things, meaning operator systems and operator algebras. So
I think that it's in 2 weeks. It's fine. It's
not next Sunday. Okay.
That's what I saw in the calendar now. But it's...
Bye-bye.
Bye, thanks, Anton. ביי חיים, דוד.
כאילו מדליקים נר ראשון יום ראשון שבוע הבא. לא יודע מתי החוק.